There are several questions in this connection where actually. So we have to start this one. F is a bounded linear functional of this. Then this one J to be the action of F on the jth basis vector. Okay. Ej or the jth basis vector. Then f of x for any x equals x1 x2. Then C f of x is equal to xj of ej. This is by the continuity of f and linearity of f, and that's now equal to j equal to xj. So from Oldest inequality, we knew that one way to get this to be a finite number of j to be a cube. So the first question we asked was, what was the first question we asked? Did have been LP. Same order. Now we will get the answer. Then the next question we asked was, what is the connection between these? These two. That is that not only they get identified, but they also get with the norm identification. The answer to this turns out to be that. On the question C that we asked, that is if f is identified with f in LQ, and G f in LP star and G in LP star is identified with G in LQ. Now what is f? Fj is equal to f of Gj and Gj will be equal to 0. The identification is through the action on the basis. Then thus f not equal to G implies the identification from it. The answer to this question is yes. Obviously, we will see that. So therefore, we got a nice identification of LP star and LQ. And the last question we asked was, is this identification what does that mean? This is given any y in LQ, does there exist f in LP star such that the capital F corresponding to little f is this y, the little f corresponding to that is E such that f of Ej. This capital F must be equal to y, that means the jth component of this must be equal to jth component of this. So the jth component in the identification is Fej, and that must be equal to jth component of y. So does there exist The answer to this question is also yes. And therefore, we are not proved all these yeses, but suppose we prove all this, then what do we get? Hence, we get the theorem, which is called the research. So at least in all these things we have to take them first to start with. If 1 less than p less than 2p, then there is this and isometric isomorphism. One more remark. If f is identified with f, G is identified with G, then f plus G will be identified with f plus G. Because the action of this on the base vector is the action of this on the base vector plus the action of this on the base vector, which is the same as fj plus gj. And similarly, alpha f is identified with alpha. So therefore, this identification preserves the vector space structure also, and so everything is perfectly matched, and therefore we have, it is called an isometric isomorphism. This isometric, there is one more here. It's that that is questioned in one way, but also an onto part. The onto part also I must have the identity. So it is isometric. The norm is preserved, and it is isomorphism. The vector space structure is preserved. This is this part, and this isometric part is that part. The norms are identification norms are the same. And this is if one level, then there is an isometric isomorphism of LP star onto. So we simply loosely say that for LP star, this equal has to be interpreted by these identifications. Okay, so that's the general scheme of things in the proof, in looking at or extracting what is this Euler space or LP. Now I don't know how many of these are proved, because these proofs are important. I want to see how it goes, at least part of it, which suggests what is happening in when you go to the integral version, LP, capital L.
Sir, is this method to identify two spaces? Like if we can establish isometric isomorphism between two spaces, then we can, is it the general method? Or?
That is general method that you can think of. One and yeah. See, iso means same. Same form. That form is the vector. Morphism is form. Iso, same form, same metric. Okay, that's what it is. So the vector space LP star is a vector space. Also, it has a norm. So it's a norm linear space. So the two structures have to be identified. This identifies the vector space structure, that identifies the norm. So without changing the metric. Isometric and isoform. Same form, same vector space form, same addition, same scalar multiplication can be identified on one side, and same length can be identified on both. That is the way of identifying. When you are looking only at vector spaces, then you are looking only at isomorphisms. But when one comes to nonlinear space or a metric space or wherever there is a metric, you want that metric also to be identified properly, and then you get the isometric case. Okay.
So open sets also will be open sets because even the topology generated by the
the topology will be same because metrics are same. So the complete identification. Convergence is identified, metric is identified, compactness is identified, everything is identified, it is the same. It only, basically what it says is the bounded linear functionals are written in Russian here and they are written in English here. The dictionary is this isometric isomorphism that translates this Russian language into English language. So nothing, they are the same things spoken in different languages. and the translation is through this dictionary, isometric response.
So here we took a specific space.
LP, yeah. Yeah, I'm looking at very, very specific actually. General structure, we don't know.
And it can go crazy.
It can go very, very crazy, extremely crazy, we may not know anything about it. What we want to say is that with the standard spaces, we are able to easily look at the structure of the bounded linear functions. Did I prove any of these questions last time? One. Huh? One answer. So what was the proof answer? I took a truncated vector and then calculated the yn or something like that. Take this vector. Certainly this is an LP because there are only a finite number of components. Sum of the pth power of the components is finite. Okay. I am going to look at this proof again because I didn't know what this is. Clearly y belongs to LP. Because summation j equal to 1 to infinity mod by j or p is the same as, and that's a finite sum. So that's why it's finite. So y is an LP. So we can look at f of y. That's valid now because f's action on LP vectors are not, because f is a linear functional on f is in LP star. So f is belongs to LP star and I define fj to be a sum. Okay. So the f is acting on LP vectors. So this capital Y is an LP vector, therefore f of y makes sense. And what is f of y? We know that f of x is summation xj, fj, fej is called fj. So now this will be summation j equal to 1 to n yj fj. Okay. So now I said that all this, what we wanted to show was the sum of the components cube power is finite. I said it's enough to show that the finite things are all bounded and then we will get it. So that's why I'm looking at the finite. So now I'm going to adjust the yj. Because I eventually want to look at sums which involve the cube power of fj, so I will get the cube power of fj here. For that, I will take f to be cube power. If I put that there, I will nicely get it. But then the problem is there is an fj here, so I will kill it. But that may create a problem because the denominator is could be 0. So let's say if fj is not 0, and 0, so now what happens? So f of y, I write it like this. What is f of y? It has to take the component yj and multiplied by fj multiplied by fj from j equal to 1 to n, because yj's are all 0 otherwise. From j equal to 1 to n only, because the other yj's are all 0. And therefore, this is equal to summation j equal to 1 to n mod fj to the power of q by our definition of yj's. Well, at least when fj's are not 0 at the time, this fj and that fj cancel again. But when fj's are 0, well, anyway the term is 0, so it's irrelevant. And yj's are 0. So this is equal to f. So f of y is a positive quantity. And therefore it is same as its modulus. But then mod of f of y is always less than or equal to the norm of f times norm of yp, because f is a bounded linear function. Therefore it is this divided by the norm will be always dominated by the supreme. And therefore, but what is norm of yp? So let's calculate the norm of yp. The p norm of, what is norm of yp? It is the sum of the components to the power of p to the power of 1 over p. So let's write what it is. Summation j equal to 1 to n mod yj to the power of p. So it is mod fj to the power of p cube, and there is also a mod fj to the power of p in the denominator. So which is simply mod fj to the power of p into q minus 1 to the power of 1 over p. But what is pq minus p? 1 over p plus 1 over q is 1 multiplied by pq. So pq minus p is q. So this is just q. Mod fj to the power of q to the power of 1 over. That's what is norm yp. I am going to substitute there. Therefore, j to the power of q less than or equal to whatever that is, j equal to 1 to n mod f j to the power of q to the power of 1 over. Now take it to this side. This is alpha. This is alpha to the power of 1 over p. So this is the alpha to the power of 1 minus 1 over p, which is 1 over q. So this is simply j equal to 1 to n mod f j to the q to the power of q. And this I can do for every n. Okay. Whatever n I want, I can go on. So this is true for every n. And therefore, summation j equal to 1 to infinity mod f j to the power of q to the 1 over q less than, and we get. So not only we get capital F is in LQ, so we get yes, and indeed mod F is. Okay. Now I want you to remember this proof. What are a few things that we have done here? Certain important things that we have done here. Then we will see what is happening. Right. Now, what about the second question? It's already there because we wanted the other inequality, which is already there. So question 2. We have f of x is summation xj of j equal to 1 to infinity by definition, and this is now in LQ, therefore I can apply Holder's inequality. So I get mod fx equal to mod 1 to infinity xj of j, which is less than or equal to summation 1 to infinity mod xj to the power of p to the power of 1 over p, summation j equal to 1 to infinity mod xj to the q to the power of 1 over p, which says mod fx is less than or equal to norm of x, which says mod fx by norm x to p is less than norm of q. So the supremum of this will be less than or equal to q. So it says the supremum is norm f. They get the same equality. So that's one inequality. And the other inequality, we got the other inequality. Yes, because norm f. So we got the answer for the second question. Right, so therefore, for every linear functional, bounded linear functional, we have identified a vector in L2 such a way the norms match. And that identification is linear. Okay? The F is identified with capital F, G is identified with capital G, F plus G is identified with capital F plus G, alpha F is identified with alpha F. So now, question 3. This is obvious. Question 3 says, F not equal to G implies the two linear functions must differ at least at one point. So, if they agree at all the basis vector, they will have to agree at all the vectors. So, they have to agree at only one, at least at one basis vector. So, it simply says, if there exists a J, that Fej is not equal to because if Fej is equal to Gij for all J, then Fx equal to Gx for all X. Therefore, F and G are the same linear functions. So, we are assuming that F and G are two different linear functions, which means the J component of F is not equal to J component of G, which means F is not. So, that's a very trivial observation that the two different linear functions are identified with two different vectors. Two linear functions are different. At some base vector, they must have a different action. If they have the same action at all base vectors, they will have to do the same. So that's easy. Then now we are left with the last question. The reverse question. Given a bounded linear function, given a function vector in L cube, so the last question, question 4, given all this while, up to question 3, we were given the linear functional, we are trying to hook up its image on the F in the L cube. Now I start with a fellow in L cube and try to find a fellow whose shadow falls there. So given F in L cube, we are trying to concoct let's call it Y then. I called it Y then. Concoct and F in L cube slot. Now, if this identification, this question itself suggests the answer. It says your F must be such that its J component must be equal to Yj. So, define Fej to be equal to Yj. Okay? Because that's what we want eventually, corresponding to, I think, erase here, that corresponding to F, that is Fj. But now we want Fj to be, Fj our definition is Fej, we want it to be Yj. So the question itself suggests what we should do. But then we must make sure that everything is okay. First of all, the moment you define the action of the basis vectors, the action of the linear function on the basis vectors, you are okay, you can define it on the whole space by the continuum. But only thing is this convergence questions will come, but we are already given y is in L cube, so this makes sense. X, y, j, j equal to 1 to infinity, Fx defines. So that makes curve. So this is my Fj. I have defined it to be know that. By holder, no everything. By holders will be. We get only this. Holders is equal to this. Normal is less than
being defined itself also comes.
yes. So holder got you this much, but what about the equality? The equality, you do the same trick as you did with question 1 again. Define now the vector y1, y2, yn and apply this and you get the reverse inequality. Okay? The reverse is got exactly as in reverse inequality. Now, got exactly as in. Remember that y1, y2, yn, you define it and mod fy and that's less than or equal to this and then everything. Okay, so essentially that's the representation theorem for LP 1 less than p less than infinity. If p equal to 1 there is a minor modification. P equal to infinity there is a huge modification. The structure is totally different. Now writing p equal to 1. Try to see what modification if at all you need. In fact, it's much easier. Okay, some of the proofs are much easier in L1 than this. You don't have to go through so much complication in many of them. But the questions will be along the same direction. Okay, question 1, question 2, question 3, question 4. Go through the same thing. But somewhere along the line, some of these inequalities will come out to you for free, almost free, very easily. My claim is show that L1 star bounded sequences, but L infinity star is not L. Now what I am going to do is only indicate the proof for LP. What is it that will go through? So now we look at the corresponding situation, 1 less than p less than infinity. Let's even look at LPAB. Measurable functions defined on the interval AB whose peak power has a finite integral. So what is this? This is the collection of all AB are real or complex valued functions such that f measurable integral mod f p dx. Let's look at the simplest version of that this representation theorem. Okay. Now same type of question we ask. Will be LP star be the LQ. What is LP star? Again, bounded linear function. With every function you associate a number and that association is such that there is an elastic limit and so on and so forth. Same, because it's a nonlinear space, the same definition goes. Analogous to this discrete case is this statement true. Now let's see, okay, we will simply try to follow the proof of the LP case. So suppose we want to follow the So what is our first step? We start with question 1. First of all, we started with given f in little LP. Let me draw the parallels here. That is, we started with given f in LP. Now we start with given f in LP star. Then we looked at right, and then let f equal to f1. And our claim was this f, that's the job. That's what all these questions were, 1, 2, 3. But the right job is done by this capital F, namely the action of the linear functional on the basis vectors carries the essence of all these things and therefore you can identify it with the vector. So now here the question was a vector was a linear functional on a vector was finally identified with a vector. Right? The linear function little f acting on a vector was finally identified with a vector which is in LQ. So now we want to identify a linear function on a function to a function which is in LQ. What will be our starting point? We have to look at it as the action of a basis vector. We don't know what is the basis vector. Here we are now in a little trouble. See, in the vector case we knew that 1 0 0 0 1 0 0 0 1 was a basis vector. So what is it? What is the role that's going to be there? We don't know. So what we do is, okay, we will put that previous fellow's proof in a different language so that probably we can identify it here.
Can we not take the indicator functions on single?
That's what we are going to do. That's the first thing we will try. The first thing we will try is, as he said, look at these LP vectors as functions. Little LP vectors as functions, as discrete functions. Functions defined on the discrete set 1, 2, 3, etc. So, one way is to look at that same thing as discrete functions defined on the set 1, 2, 3, etc. Then the basis vector Ej is nothing but that function which takes the value 1 at j and 0 elsewhere. So let's copy that. See what will happen. So let's copy Ej as a function which takes value 1 at the function Vjt at t equals to j and 0 elsewhere as a function on m. Vjt is defined only for n equal to 1, n equal to 2, n equal to 3. So it's a discrete function which is defined as that Ej t is equal to 1, t equal to j, 0 otherwise. Suppose now we want to do this in this case. Here, if we try to do this, we have already a slight problem. We want to take it 1 at 1.0 elsewhere. But then that is 0 almost everywhere. If you take a function which is 1 at 1.0 everywhere else, that's a function which is 0 almost everywhere else, but it's 0 function. So you are not getting anywhere. Right? So the thing is, try to do this, the function which takes 1 at a point, which takes the value 1 at a point, 0 elsewhere, is 0 almost everywhere, because singletons have measured 0. So 0 almost everywhere, you haven't gone anywhere. So it's a 0 function. It's a 0, it is equivalence class. So it is only, you are simply hanging around the 0 function only. And I already know the action of a linear function of 0 function is 0. There is nothing new that you are going to get out of it. The linear function's action on the 0 vector is 0. So this is the 0 vector only, and you are not getting anywhere. So here is a problem. So therefore, so again we backtrack. So we have to look at how we should interpret this. See, the world of impulse is taboo. Better 0. You see?
The action of the functional on this Cj is 1 at the point. We define it.
The action of
The functional on
I can write f of x as integral f and delta dx.
But that integral again doesn't make sense. What is delta? First of all,
No, the delta measure coming from the delta.
Measure coming from the?
I can write that Lebesgue integral, right?
That's not Lebesgue integral. That's a different integral. See, we would like to get this If you want to get the corresponding result, you should get a given an app. Our aim is to get an app which is in Q such that the action of f on any functional g is a to b gx fx dx and all are level integers.
So it's right.
See, the moment you bring in delta measure, you are making the f as a delta function. That's where the problem. It's okay, it works, but it's not acceptable as a mathematical proof.
So f of a function is a number, right?
Huh?
The linear function is acting on a function.
Is a number.
So such numbers collected should give us a function in anything.
That number?
Collected
Yeah.
should give us a function in capital F. In this case.
That's what we are trying. We are trying to find a representation for that. The question is, should I collect all that?
I should certainly collect uncountable numbers.
See, in the vector case, it said if you collect only those on the basis vector, it's enough. Now, how do I interpret this? That basic part of it is a little bit complicated again. It's not letting me go anywhere. Yes.
F1 we got for EJ,
Yes.
F2 we got for E2,
Yes.
and all that. So now instead of taking G, I will take G to be unit function.
G to be one throughout one. Throughout one. That is function is equal to 1 for all t.
Yeah, G to be 1 for all T.
Yes.
So F of that should give F capital.
No. That is only one function, no? So the action of the linear function or one function will it decide. It's not possible. Okay? That's also another. In other words, you are saying the vector case, if I take the value of the functional on the vector, all of whose components are 1, I will know the functional. That's not correct. That's
So
also.
here in translated version of this unit function, they form no basis.
You go ahead, you are on the right track, tell me.
So, I mean, by taking a sequence of these functions, this will be tails for all continuous functions.
That's the idea. I mean, essentially you have to get to that level of density arguments. Okay. Okay. The way they do it, it becomes very technical. All this try leads you to something. So let's backtrack and see what's happening. You are in the right track. Now we'll get into some technical difficulties of writing this integral. You have to sort it out, eventually get the proof. Your track is right. You have to now shift this unit intervals that you had, or some intervals, take the characteristic function. Instead of taking 1, see, if I take the value as 1 at one point, I am in trouble. If I take value 1 as in some intervals, characteristic function of an interval, then that makes a little bit of sense now. And look at the action of that, and then try to manipulate with such action of f on such characteristic functions. Essentially, characteristic functions on suitable intervals. That's what we are going to do. Now, why do we do that? Even then there is a slight problem. So what we do, we backtrack, and all this going forward and backwards, finally we get the idea of what is to be done. So what I looked at it is the following. Now let me get to this idea itself first. Let's look at it this way. My idea, it's not my idea, it is to get an F in Q, A, B, such that my first requirement is this. The action of f on G can be written as this. This is the one corresponding to this. Fx equal to xj fj. The action of f on a vector is the value of the vector at the point multiplied by the value of this function f at that point. So the value of this vector at this point multiplied by the value of the function at that point. There it was a discrete sum, now it's an iterative. So this is our aim. This is what we want. Okay. Now, suppose I can get hold. This is where the trick of the integrals coming, the way we define integrals. Suppose I can get an f. We will worry about the norm and other things later. We don't even know whether we can get such a representation. Then we have to worry about whether the norm of this functional is the norm of that function here. All that questions we will ask later. First of all, we will ask whether such a possibility exists or not. Suppose I can get an f in LQ such that Fg for all for every measurable for all simple functions. For all simple functions. Suppose this is true. When will this be true? Suppose I want to make f of g to be equal to integral g times capital F for all g. But suppose I can make it for simple functions.
Basically, G we have to make it as a summation of simple functions, and then the limit and then.
So any g can be thought of as a limit of simple function. Any g in LP is measurable. If it is measurable, it is the limit of a sequence of simple functions. So if we have a sequence of simple functions going to g and f being continuous, somehow I have an idea that I can push the limit inside and I can get the representation for the general functions also. So there is a hope. Okay, we may be used to able to use some convergence theorem, continuity of f, etc., etc. Then, okay, let me write that. Then, given any g in P, can find Gn simple such that Gn contains P. Then we have Fgn is equal to integral a to b Gnx fx dx. By this, suppose I can have, okay? Suppose I can have Fg is equal to g fx for simple functions, and therefore Fgn will be equal to integral Gnx fx dx, and therefore limit n tending to infinity of Gn will be equal to limit n tending to infinity a to b Gnx fx dx. But this is equal to Fg. Why? Because of f being linear, you would like also this to converge in LP. Suppose we can get a convergence in LP. F is continuous, I can get this Fg and use some convergence theorem to push this inside the integral and write it as Gx. So there is a hope that we may be able to do such things, manipulate with this convergence theorem, use the continuity of f, use the fact that I can approximate by simple functions, and therefore if I get hold of for simple functions, then there itself I stop. If I can get hold of an f such that Fg is equal to integral g capital F for simple function, I am now happy. Therefore, but simple functions are made up of characteristic functions. So it's enough if I show it for characteristic functions. Okay? Now the next step therefore is, suppose this is step 1, this is 1, this is 2, this is 1. If 2 is true, 1 is 1, there is a hope of getting it for 1. So now I do 3. Suppose I can get f in LQ such that f of g is equal to integral a to b fx dx for every characteristic. Suppose I can get it for every characteristic function g. What is that mean? Characteristic function of a measurable set. Okay. Now, but this is once that is true, this is made up of finite number of characteristic functions and constants. So integral of a finite sum will be the sum of a integral. So I can push everything will go. So then 3 will imply 2. Then 3 will imply 2 because simple functions are finite linear combinations of characteristic functions. So therefore, my aim is only to get this. Some or the other cook up and get an f such that f of g is equal to integral g of is valid for characteristic functions. Even then I don't need, because whenever I'm a finite interval AB, it's a finite measure space. What is the characteristic function? Which takes the value 1 on the measurable set E and 0 elsewhere. Now, if you have a measurable set with finite measure, then it can be approximated by a finite number of intervals. One of the first regular theorems we had. Any set with finite measure is essentially a finite number of disjoint intervals. So, what is the recall? Any set A with measure of A finite for any set, there exists I1 and for any epsilon positive. There exists finite disjoint intervals I1, I2, Ik such that the measure of j equal to 1 to k ij delta A is less. That is, what is extra coming in this union, what is left out from A, all that thing put together, the error is less than epsilon. So in other words, what it says is that a finite measure set is essentially a finite number of intervals. So using this approximation, it looks like it's enough if I show characteristic function of a finite number of intervals is enough. Basically that is a step function. Okay, so basically therefore, if you take characteristic function of an interval and if you can do it, basically you are done. So therefore it looks like, step 4 looks like if we show that f of g is equal to integral a to b f x dx, so that we can get f in q like that. The characteristic is equal to for g is the characteristic function of an interval. That's why we are slowly heading towards. This is the reason why it all comes to the characteristic function of an interval. Then we will have this implies 3, which will imply 2. These are all hopes. So therefore it looks like all you have to do is look at characteristic functions of intervals. Characteristic functions of intervals in AB. Now suppose you take an interval in AB, some interval, closed, open, whatever it is, RS. Okay? You take any interval in that AB. I want to look at that function which is 1 there and 0 elsewhere. So if I concentrate and focus on such functions, I seem to be having step by step building up the entire result. Okay. Now if we concentrate on this function, you observe that if you take up to R and then up to S, the characteristic function of this and the characteristic function of this. How is it connected with the characteristic function of this? That minus this. So therefore, it says enough if you look at characteristic functions like this, which are starting at A and ending at R. So finally the problem boils down to that. So therefore, so any such function, any such characteristic function is the difference of characteristic functions of the type A or all we are not saying whether it is an open interval, but does it matter? They are all one point will be set of matters 0, so it's irrelevant which interval you take. But anyway, generally. So therefore, the final clinch is therefore look at intervals of the form A. Okay, I will not write open, close. It starts at A and ends at T. Okay. Starts at A and ends at T. Where T is less than what does this mean? So now let us go backtrack. Did we do anything like that on the little LP case and the discrete case? Did we do anything like that at all? Pardon me? Yes. From the beginning. See, that's the important thing. So what did we say? Suppose I take now 1, 1, 1, 1, etc. 1 and then there's 0. This is now a counterpart of that. Start at A and up to some point you take 1 and all others 0. Now up to some point is now discrete points. That is the one the discrete case, this should have been the local viscous. So but then what we did was we didn't look at it. What did we look at? But this is nothing but the difference of such two fellows. This is nothing but the difference of two such fellows. So suppose I take Ej, it is nothing but Ej plus 1, Ej minus 1. Ej minus 1. Not Ej, what should I call this? Gj. Gj minus Gj minus. This sort of characteristic functions. But Gj minus 1, you look at it as the difference. What do you call it? The numerical the discrete difference. You have made one step extra and see what is the change in the value of the function. Now that is the discrete version of the derivative. Gj minus 1 by 1. Now you look at these fellows, look at the action of f on this characteristic function, look at the derivative. You will get the correct. So that's exactly where they hit the jackpot.
So if I complete that is an impulse and all that.
Pardon me?
We are saying impulse, we are saying derivative of
Yes, exactly. The impulse has to be brought in with the correct meaning, and that's how it goes. Okay. So therefore, what they do is the following. This is the proof. This is all the proof. What the proof is, now I will formalize this. The way to do it therefore is, you just write the main ideas. Main idea is, so now, F in LP star is given. Okay. Now I will use some notation for this. Let Gt for T into B. Let Gt be the characteristic function of A. You will see the reason why finally I put open in there and close there and so on. It will come out automatically in the explanation. GT with this characteristic. Now I want to look the action of F1 GT. This is in LP because it is simply integral a to t 1 to the power of p dt, which is t minus a less than under b minus a. So GT belongs to LP. So look at this is a number, the action of any function, but this number depends on t. So for every t, now I get a number. So this gives a number. For every t in for every t in AB, I get this number. So in other words, I have a function. So we have a function h of t defined for a less than b less than equal to t as h of t to be the action of f on g. Alright, this is where that our f is going to come through this, the derivative of this. But I have kept my options open for h of a. Okay. We will see that this helps. We define h of a to be equal to 0 so that we have h mapping from a b or similar. So now we have got this function h. Okay. Now the ball game starts. You want to talk about its derivative. Remember that the difference has to be interpreted as the derivative, the action. If you didn't think at all these questions will start happening. Turns out to show that even if it is differentiable, we have to look at the integral of the derivative. Okay. So all that comes, h is absolutely continuous. See our old things will come. And fundamental theorem will say h of t minus h of a is equal to integral exponent t t a. And in order to avoid this term, I chose h a to be 0. So that is so h t will be equal to integral a to t h prime t. Now claim the rest of it is verification. This h t h prime t works as well. See, what is happening is, you are right, you are absolutely right. Well, you said that, sir, I will write it as respect to some h measure, not the Lebesgue measure. Now that measure has a density, capital HT, and so it will be h prime t dt, and the density was what they were looking at, and that turns out that it has a density, and all that manipulation works, and the rest of the game is only technical verification that all this works, right, inequalities, etc. But the idea is how you look at the discrete case proof and go on asking, banging it to the right way and get it. Because another way would have been if you would have started off with a right shoulder basis. Whether there is a shoulder basis for LP. If that had been there, then that would have been very nice. And that way also you can do it. Okay? It's not. So this is the idea of the least representation. Capital idea. The idea is, given the linear function, look at its action on these initial segments, characteristic functions of the initial segments of the interval A. From that thread takes you all the way. From that it tells you that I can construct it to be, say, good for characteristic functions of intervals, and therefore the characteristic functions of measurable cells, and therefore the simple functions, and therefore very important. This is the sequence. We are thinking of proofs in this integration theory always like this. You always look whether it is true for a very characteristic function of an interval. If it is true, you have hope. If the result is not there, don't even think of looking at a general point. If it is true for an interval, then try to push it for a measurable set. Then from a measurable set to the characteristic function of the measurable set. Then simple functions. Then to the... So all these places, some convergence theorem, some regularity property of the... See, all of these problems would be really messy if you had a complicated measure which did not have this regularity property. That the measurable set is essentially a finite number of disjoint intervals. If you had some other measure which did not have this property, you would be in trouble. This proof would be in trouble if it did not have finite interval. See, I have taken a case where the essence of the proof is easily seen without worrying about those techniques. Then what you do is for an infinite interval, it is called sigma finite measure. It can be put as the union of a finite number of measure spaces and try to add up all these things and you get the result. Okay. So many of these theorems you need not worry about R. If you have it on finite interval, use the sigma finiteness of the measure is right to get for the general case. But the finite interval case, the key is, does it work for characteristic function of any interval? And therefore characteristic function for the initial segment interval. If it works, if it doesn't work there, don't even hope for that theorem. If such a result seems to be reasonable for characteristic functions of these initial segment intervals, then try to see whether you can push it to the general case. If it is failed this is the foundation stage. The foundation is weak, there is no point about that theorem. So there is always, if you have a hunch, there may be some result like this. See whether it is true for this simple case. If it is not even true for this case, don't even bother to waste your time trying to prove it. That's the idea of this course. Okay, any questions?
So why does H pen will I go to LQ?
You have to show that. You show that H prime in LQ or not. Even if the derivative that was in LQ, even in the discrete case, the difference we got, which he gave you F1, F2, Fj, that was in LQ. That's exactly what you said.
So that equation Fg equal to integral a to b f of x g of x, that
Yes.
here. Was that?
Yes.
That is, if you treat g as the input to an LTI system,
Yes.
then f of g is the output.
Yes.
And that is the impulse response.
Yes.
So that should resemble a convolution integral, right?
No, not necessarily. See here, the output is a constant C. It's a number.
You can then add 0, like a shifted 0.
Exactly. So it's enough if you look at the signal at the point 0. There it's enough. So therefore, see, most of the times, the finite dimensional case suggests the proof for the finite dimensional vector thing suggests the proof for the infinite component vectors. There are some technical things you have to take care of because of the convergence, etc. You put there too. Now to go from this discrete case to the function case, you have to really interpret them no longer as vectors but functions on a discrete space and functions on a continuous space. What is the corresponding role of this in the general case? This difference is the derivative. And from then on you have to pick up. Okay? This has to be interpreted as initial segment characteristic function and then its derivatives and then go ahead with this. So that is how the proof has to be seen.
These are also isometric and isomorphic, this identification.
Yeah, again all the other questions will come. Once you establish this question, the rest of them will be very trivially following like the exactly the previous. This is only the same norm we put, the same inequalities will work. Holders is also here because we have proved Holders inequality even in LP spaces. So all these things will now, the rest of the game will be The key is to capture the capital F. The moment you capture the capital F, the rest of the ball game is the same. It was in capturing where we saw it very easily in the discrete case as the action of the functional on the basis vector. Here you have to see it as a little box. In other words, what we look at it as follows. Why did we look at the basis vectors? Because it is a good sampling. If I had sampled on that, I could get answers everywhere else because everybody else was a linear combination of it. But because I don't know a basis yet. So therefore I don't know what is. So I want to forget about basis part and think of it as sampling. Which is a good population to sample? Now the development of the integration theory tells me the good population to sample is the simple functions because others can be built from that. And then the simple functions can be got by characteristic functions because that's a good sampling. And the characteristic functions can be got by these intervals and therefore that's a good sampling. And the intervals characteristic can be got by characteristic function of the initial segment. That's the good sample there. And that works. Okay. So if you look at it that way, so it may not be the best sampling. You see, what I am trying to tell you, that may not be the best sampling, but still it works. We may be doing a little more work than is necessary because there may be a discrete basis. There is. Okay, there is a shorter basis in which you can work and then it will give. But still, for me, a theorem I can get without worrying about the basis. I know one sampling which leads me to the result. That's all. So whether your sampling is the most optimal sampling is a different ballgame altogether. Because here already I am doing an uncountable sampling. A to T, as T varies from A to B. Yeah.
So if you get hold of a shorter basis, the proof is more or less photocopy.
Yeah, but there will be slight some technical difficulties because even if you get shorter basis, what about the coefficients in that expansion? They have to be right. See, if you get hold of, okay, so you get hold of, let me write this, suppose we had LP, okay, and we had LP star. We had LP. This is exactly like the picture we did for little l. Now we started off with one LP. Now suppose you had a shorter basis. Suppose you had a shorter basis and control of FE1, FE2, FE. See, I haven't got a shadow here. Right? How do I get that shadow? Then I must calculate my shorter basis here. Then try to construct a vector here through them, namely capital Fx to be equal to Fe1 times E1x plus Fe2 times E2x and so on. Hopefully this will be. So for this to happen, these coefficients must be well be here. So that expansion must be well be here. So there must be certain shorter basis which maintains all these things. So there will be an initial identification to something, a sequence of vectors here which are right such that they lead you to a vector there. So these coefficients must be such that this belongs to.
They are again more or less the step functions.
Not necessarily step function. There are what are known as, for example, your shorter basis, for example, if you have a shorter basis, okay. We call this absolute shorter basis if x is equal to summation xj aj for every x such that so that now the coefficients will be identified in L1, little L1. Okay. Now some kind of L identification. If it is called a Rees basis, that's fine. In other words, that will identify the vectors with little L2. And in general, we can put P Rees basis. So, the shoulder basis that we get hold of must be so adjusted that these coefficient vectors form one of these, that is, this is a P shoulder base or R shoulder basis for some suitable R, which makes this conversion easy. Okay. So there are so many things involved. There must be a shoulder basis here, a corresponding shoulder basis here, which together adjust those coefficients to this identification. Then all that you do, that proof works. Hilbert base is very easy. Everything falls down to the same thing, and therefore H will be identified little h2 and little h2 back identified with capital H. That is the situation. But the idea is very common sense. I mean, eventually, if you look at all these proofs, the idea is common sense. You just have to bulldoze your way. What works? What is it that will work? And what is the least I have to do? See, I am also lazy. What is it the least I have to do? The least I have to do in the discrete case is look at the basis vectors. The least I have to do is do the sampling that I know. The sampling that's suggested by the construction of the integrals is look at simple functions and therefore look at characteristic functions of measurable sets and therefore look at characteristic functions of step functions, intervals, and therefore look at characteristic functions of initial segment intervals. And that works. So once I have my problem well posed, this is what I have to do. If this much I do, the rest of it is available for me. And therefore I do this and it works. Okay. So that's why they say problem well posed is half solved. You know now exactly what you have to do. And you do it and it works. Okay, I think this is the right place to stop. Next week I will not be here. I will not take the classes, but we will resume the week after. I will look at all that number of shoulder basis cases, and in fact I will probably even mention what is again more precisely what the shoulder basis problem was. I discuss shoulder basis. Probably you can look at many shoulder bases, L1, L2, LP, what are all the shoulder bases. Explicitly we will look at it.